All right, so reminder, unit exam is Wednesday, May 25th. Okay, so it's coming right up. And your review package was posted in Google Classroom earlier in the week. Definitely have a look at that. Most of the questions on there are old exam questions, so it'll give you an idea of the type of thing I'm going to ask. Okay. So first thing we went over in this unit was the types and forms of energy. Okay? And that is something that will appear exclusively in the multiple choice. All right, so, let's say, put a picture of a wind turbine on there and ask you, what type of energy will this wind turbine generate? You would say electrical, or what kind of energy is it using to generate electricity? And you would say mechanical, okay, or something like that. So be able to identify a form or type of energy from a picture or a description of it. Okay. So the things we went over there, also systems, open, closed, and isolated. We talked about those on the first day. There'll be a couple of multiple choice questions about those. Remember that an open system can exchange matter and energy with its surroundings. A closed system can exchange only energy with its surroundings. And an isolated system is completely theoretical, but would exchange nothing, neither energy nor matter with its surroundings. Okay, thermodynamics, we talked about heat engines, we talked about the first law of thermodynamics, which is just the law of conservation of energy. We talked about the second law of thermodynamics that tells us energy flows from hot to cold, thermal energy, okay, mechanical energy from high to low, okay, things like that. So understand how those things work, so just have a read over them in your notes, because again, it's strictly multiple choice items where you have to recognize the correct answer. Okay. And we also talked about how perpetual motion machines are forbidden by both laws of thermodynamics. Okay, in order for one to do any work, it would have to create energy, which would violate the first law, and they're always losing energy because of the second law, and so therefore they cannot function. Okay, guys, don't be afraid to ask questions as we go here if you got some, okay? Then we talked about scalar and vector quantities. This will be important in both sections of the exam. There could be some multiple choice questions, such as saying, which of the following is a scalar quantity? Okay, and there would be 4 listed, only one of which would be scalar, okay, or which is a vector quantity. But the more important reason you need to know which things are scalar and which things are vector is for the written response where you're doing problem solving. So for example, if I was to give you an acceleration problem, and I give you that the object starts from rest, accelerates at 2.5 meters per second squared for 5 seconds, what's its final velocity? What do you have to, sorry, and I should say the acceleration was north. What do you have to remember to put on your answer?
Yeah, it was moving north.
That its final velocity is north, because I asked for velocity, not speed. Okay, so in that case, you have to remember velocity is a vector quantity. If I just solve for velocity, I'd best put a vector on it, lest I lose a mark. Okay, so that would be the more important place. In addition to that, graphing and problem solving, if I give you a velocity north and then I give you a velocity south, you have to remember that one of those is positive, one of those is negative. Okay, that's what any kind of by scalars and vectors.
So to write the vector quantity with velocity, we actually add if the direction is given.
Yes. Well, if no direction is given, then it could be positive and negative. But
like
on the test, though,
we've been solving for velocity past couple days.
We haven't been solving because we've been using work and energy. I may have accidentally used the term velocity a bunch of times. I apologize for that. Speed is what we're dealing with when we deal with work and energy, because energy is scalar, work is scalar. Okay. So remember when we did the question about the person who jumped out of the plane yesterday? Okay. When they jumped out of the plane, they were moving horizontally. But it didn't matter. If they'd been moving vertically or diagonally at 90 meters per second, they'd have the same amount of kinetic energy regardless. Yeah. Okay, so the quantities that we went over were as follows. Okay, our scalar quantities, okay, are speed, distance, time, and energy. Okay, and then our vector quantities are velocity, displacement, acceleration, and force. Force is basically not going to come up, but if this was a multiple choice question and I was struggling to get a third item or fourth item, it could pop in there. The first place we used scalar and vector quantities, or the first formula where it was important, was V equals D over T. Okay? So we have to remember that there's actually two versions of that. This one, that solves for velocity using displacement divided by time, okay, which is final position minus initial position divided by time. And then the scalar version, speed equals distance divided by time. Okay, I'm not going to have on the exam any of those like 2 or 3 part V equals D over T questions like we did in class, but you could possibly run into using this formula in a graphing situation. Okay, where you have a graph with multiple parts, like a position versus time graph or something like that. Okay. So definitely still know how to use that formula, but I'm not giving you a 5-mark problem in the written response to do with V equals D over T. Okay. You guys are past that. Okay, graphing. There's lots of them. In the written response, there are both kinds of graphs. Okay? There's one question that has a position versus time graph, and there's one question that has a velocity versus time graph. So you're going to be asked to do the same things you were asked to do in class. Okay? That would be use y equals mx plus b. Right? If it's just one straight linear graph, I will have the equation on the graph. Okay? If I give you the equation on the graph, should you use it to answer the questions whenever possible? Yes. Okay? If you are given y equals mx plus b for the graph, use y equals mx plus b to solve any questions with that you can with. Okay? Make sure you do that. Don't try and do it some other way. I will have set it up so that you will get the wrong answer. Okay? What does M stand for? Slope. Okay. On a position versus time graph, the slope represents what? That's on a velocity time graph.
How is your position changing?
How fast your position is changing. How fast your position is changing is velocity. Okay? Remember that this is something you don't have to memorize, it's something you can figure out. Okay? If I'm solving for M on a position versus time graph, y is my final position, b is my initial position, x is time, I'm solving for velocity. On a velocity versus time graph, this same formula is now going final velocity minus initial velocity divided by time, which calculates the thing you told me first, acceleration. Displacement, remember, is average velocity times time. That's the shapes, the area here. Okay? So those are all things you are definitely going to be asked to do on the unit exam. Okay? all the same things you were asked to do in your labs. So not a bad idea to look those over as part of your study. Okay? All right. So let's say I have this equation here. What would that graph look like? Right. What's that? 38. Yep, that's B. Okay. This would be 2.5, negative 2.5. Okay, and any point along it would give us a y and an x value. Right. So just being able to read a graph, being able to interpret a graph. If this was a position versus time graph, this object would be doing what?
Would be calculating the range of point.
I hate it when that happens. It happens more as you get older. Sorry about that. I won't lie to you though. Okay, so this object's position is getting,
Isn't it like going back?
Yeah.
towards emissions with this?
it's going backwards. Okay, it's going backwards at a
That's just it.
constant velocity. Okay, remember, if I gave you that on a test and said, what is going on in this graph, for full marks, it would be moving backwards at a constant velocity. If you said moving at a constant velocity, you wouldn't get full marks. Backwards is important. Okay, everybody follow me on that? So being able to interpret a graph is still an important part of this. If this was a velocity versus time graph, what would that object be doing? Negatively accelerating. Which direction is it moving? Forwards.
It's just going slower.
Yeah, it's still moving forwards because its velocity is still positive. Okay, it would be moving backwards if I extended the graph. There it would start moving backwards. Still accelerating backwards and now also moving backwards. Okay? All right. The next thing we went over, okay, and I know I've got a few sample graphs that we're going to do here in a minute just as a review. But the next thing we went over was acceleration. Number 2. Shoot, I changed it so many times now I don't remember. I'll go over it here with you in a minute. But there's definitely at least one acceleration problem, if not 2 acceleration problems, in the written response. Okay, so a question that's going to ask you to use A equals VF minus VI over T. Then we went over work energy theorem. There are 2 work energy theorem problems on the exam, 1 potential and 1 kinetic. And they are of a very reasonable level of difficulty. We have done many in class harder than the 2 I put on the exam. Okay? So they're not going to involve like crazy manipulation. When we're looking at a work energy theorem problem, how do we know it's work energy theorem and not conservation of energy?
Force or distance are involved.
Right, okay, we definitely have force involved, because distance we could still misconstrue as like a change in height or something like that, so, but definitely this is something that won't be in a conservation of energy problem. Neither will the word work. Okay, and in a work energy theorem problem, only one kind of energy is going to change. In a conservation of energy problem, both the height and the speed will change. Okay, so that's how you can kind of tell them apart. Okay, if you're struggling to tell them apart, that's how. Also, I did not use a new context for the law of conservation of energy problem. It's something that we've done before in class, and you should recognize as a law of conservation of energy situation. Okay. Alright, that means this thing's law of conservation of energy. So I equals EF. And from what I've seen, you guys are pretty good at this, so should be some easy marks. My suggestion to you for the law of conservation of energy problem is this: show all the steps. Okay, it's out of a fairly large number of marks, thus each step is worth something. If all you show is your final answer and it's wrong, you'll lose out on a lot of marks. So show your work. Okay, and then lastly is efficiency. It's only in the multiple choice. Okay, there's a very simple, like, problem-solving thing in the multiple choice. Okay, and it's, remember that efficiency is the work done divided by the energy put in.
The conservation of energy, is that what it's still?
One. Okay, and I think those numbers are right. 20 multiple choice, 7 written. And the written are problem solving. Okay. Okay, so let me get the test open here, guys, and we'll have, well, I will, not you. Sorry, I got your hopes up there. That was me. What's that?
If you actually feel like a bit much farther behind you, or you can say reflection of reflection.
Yeah, maybe that's why I can do that. Okay, so all the formulas that are on the back of your periodic table are on the front of the exam, so you won't have to have your periodic table / formula sheet with you. Everything you need is on the front, including the efficiency formula. Okay, so yeah, 20 multiple choice questions, and like I said, there's some terminology like what's work, what's energy, those types of energy, the thermodynamic stuff, the systems. Okay, quite a bit of stuff actually on thermodynamics. Some very basic V equals D over T calculations, like very basic. There's a graph, but again, it's a very basic graph. I would also suggest that you have a look at the very first thing in the acceleration lesson, and that is the definition of inertia. We talked about it briefly, but we haven't really returned to it. Okay, the tendency of an object to continue doing what it's already doing. Okay, like that's why the desks don't just spontaneously move. Okay, there's a very basic acceleration question, and there's some questions that ask again about mechanical energy, about thermodynamics. They don't involve any calculating, they just involve demonstrating your understanding of how things work. They're situational type questions.
Test is approved by my own computer.
Okay. And actually, I forgot, I took the calculation question for efficiency off. So you only have to know what efficiency is. You won't even have to do a calculation with it.
How much is the entire test worth?
The entire test is out of 65. Okay, so as I was saying, graphing is a fairly significant portion of the test. Okay, I'm looking at here 7, 10, 16 marks out of 85, out of 65. And, no, sorry, 17 because there's one in the multiple choice. So 17 marks out of 85 are, or out of 65, sorry, keep saying 85, out of 65 are on graphing. Okay, and it's exactly what I just told you. You're gonna have one graph where there's a y equals mx plus b situation, and there'll be another graph where there's not one single line but many parts. Okay, and there are two acceleration problems. Okay, and as I said before, 2 work energy theorem and 1 conservation of energy. Okay, so let's look at a couple things like what you might see. Write that one down and give it a try. See if you can identify what kind of question it is and solve it, because that's what you'll have to do on Wednesday. What are our givens on this question?
It's initial velocity, it's time of flow, and the force it's, yeah, gravity.
Okay, those are our givens. That makes this what kind of question? No. It's an acceleration problem. Okay? How do I know it's not a law of conservation of energy problem? Well, we never have to find distance in law of conservation of energy. We might have to find it in work energy theorem. Okay? But here's how I can tell this is not a work energy theorem problem and how it's not a law of conservation of energy problem. Am I given height in this question? Then it can't be either one. Okay? If it was law of conservation of energy, it would have to have at least one height, and I'd be looking for the other. Okay? Or it would have 2 heights and 1 speed, and I'd be looking for the other speed. Okay? This doesn't give me that. It just tells me it's dropped, and I'm looking for how fast it's going 8 seconds later. Am I ever given time in any of those other questions? No. Okay? Time is never a given in a law of conservation of energy question, nor a work energy theorem problem. Okay? As a result, this is an acceleration question. Okay? Because I was given time. So A equals VF minus VI over T. And that's kind of the thought process you have to go through. All right? You're getting several different problems on this unit exam, and you've got to be able to identify which type. Okay? This one would be easy to mistake for a law of conservation of energy question because gravity is involved. Okay? But it's not conservation of energy. All right. So I'm solving for VF, so I'm going to multiply both sides by T. VI is 0, so I'm not even going to bother doing anything with it. Okay? All I have to do is multiply A times T, so it'll be 78.48. Oh, what do I need to have on this?
A plus. Oh.
Last time I checked, things fall down. Well, let me check again. Yeah, still true. Okay, things still fall down. Okay, so how easy would it be to miss that? Really easy. I almost missed it. Okay, it would have cost me a mark because I had an answer that was not a vector quantity when it asked for one. Okay, that's exactly the situation I was describing to you there when we were doing the review. Okay, all right. So that's one example of a question you might get. What kind of question would this be? conservation of energy. Roller coasters are always conservation of energy questions. Okay? Go, give that one a try. This one. So it's a law of conservation of energy question. So we start out with this, EI equals EF. Expand it out to initial potential plus initial kinetic equals final potential plus final kinetic. Okay, and we are looking for the initial height, which is part of this. So we want to subtract the initial kinetic over to the other side. So we'll be left with this. EP final plus EK final minus EK initial. Okay, and then we can expand it out further. M times G times H initial equals M times G times H final plus 1/2 MV final squared. Okay, minus 1/2 MV initial squared. M's are going to cancel because they're in every term, because I don't want to put in whatever I said, 2 million kilograms. Okay, and then I'm going to divide both sides by G. That'll leave me with HI. Okay, so HI will be 9.81 times 8 plus 1/2 times 21 squared minus 1/2 times 5 squared divided by 9.81. Comes out to around 30, I think.
Oh,
I had 29.
29 point?
29.2.
Yeah, I think that's what I had. We'll double check it here.
I've got 21 as well.
Okay, so 9.81 times 8 plus 0.5 times 21 squared minus 0.5 times 5 squared divided by 9.81. 29.2 meters is the height of the first hill. Okay, questions on that one? Anyone need that? Anyone? You guys are so lucky that you can do that. I would have killed to be able to do that.
Do what?
Just take a picture of what was on the board. I had to scribble like crazy, and with my penmanship, my notes were useless. Okay. Laws of thermodynamics. Okay. Hot to cold. That's the natural flow of things. That's the second law of thermodynamics. Okay. If I have a cold area and heat is being pumped out of it to the hot area, that's being done by a heat pump, like a refrigerator or an air conditioner, okay, that uses energy to go against the second law of thermodynamics. Okay, so here's something I might ask on a unit exam. Here's a position versus time graph. There's the equation, y equals 2.7x plus 0.309. I would like you to calculate the position at 30 seconds and time to reach 100 meters. How do I go about solving all three of these? What do I use? The equation for the line. Okay, this is what I was talking about before. If I give you a graph and the equation for the graph's line, use the graphing equation for it. Okay? If I'm looking for the position at 30 seconds, I'm solving for a y value because position is on the y-axis. That's why that one's only out of 2 marks. It doesn't require you to manipulate the equation, just to plug the numbers in. Okay, so for question number 1, you're simply going y equals 2.7 times 30 seconds plus 0.309. Okay, so 2.7 times 30 plus 0.309. Okay, 81.309. Meters would be the position. Okay, so you get 1 mark for your work and 1 mark for the answer. Question number 2 is asking you for the time. It's asking you for an x value, which means there is a manipulation of the equation involved. X equals y minus b over m. So that'll be 100 meters, because they wanted to know how long it would take to reach 100 meters, minus 0.309 divided by 2.7. Okay, and make sure you do that subtraction operation before you divide. Oh, 2.7. All right, so we'll be looking at 36.9 seconds. Okay, why is number 3 out of only 1 mark?
Is the velocities, the slopes, or 2.7?
Right. It's basically asking, can you identify or do you remember that the slope of a position versus time graph is velocity? That's it. Okay? So, you would be surprised, guys, when I ask that question on a test, how many people show me 3 marks worth of work? That's all wrong. Okay? That is a recognition question. So, as a test-taking tip, this is for my tests, if a question is out of 1 mark, there's no work. The answer is right in front of you. Okay, so that's a little tip, test-taking tip. Okay, last one, because we're running out of time here. You got a velocity versus time graph. I want you to calculate the total displacement of this object. Okay, total displacement of this object. I'll give you 3 minutes. It'll take me 1 minute to do it, and then we'll be out of time. Hmm?
Did you ask for 4 minutes? No, I wasn't.
Yes.
Oh, boy, I made that graph terrible.
I was looking at it.
-4. That's probably 9.
Probably.
Well, that's what we're going to say. That's the numbers I'm going to use. Okay, and then this would be at 5 seconds.
Unless part of this
Right.
displacement.
I want you to find the displacement, and then this would be at 7 seconds. Okay, the x-axis, guys, is right here.
Oh.
Okay, that's the x-axis. Make sure that's important.